for coming. We are aware that it's very close to the XMM deadline, so thank you for taking time to show up. Today is our pleasure to introduce Xiurui and also Shifra, who will give the second talk. I'm going to introduce our first speaker today. Xiurui was a postdoc at the CfA between 2021 and 2023. And he was a pre-doc also at the CfA between 2020 and 2021. He's currently a postdoc in the high energy group at Cal-10. Xiurui obtained his PhD at Clemson University in 2021. He's interested in high energy astrophysics, including supermassive black holes and stars. And he's also interested in extragalactic surveys and time domain astrophysics. Today, he'll be telling us about probing AGN Coronae with high-redshift AGN, and be aware that he's also giving a talk at the head meeting, so you can ask him about that. So take it away, and thank you.
Thank you so much, Johannes. Can you hear me well online as well? Okay, thank you. So it's really a great pleasure to come back and do the really familiar high energy seminar. So today I'm going to talk about the AGN Coronae, and we make it a name of PACHA, which is the space-time in South American language. So it's a really nice name. And so a collaborator with Clemson, Italy, and also here with Martin, and also from Caltech. And the background is our recent JEPC program on a North ecliptic pole region called Nexus. It's a 300 hours JEPC monitoring program, and this is the first image we got early this year. So it's just making me feel like the universe is so astonishing. But anyway, so Coronae. So what do we know about Coronae currently? So to be honest, I want to put a blank slide thing. We know nothing about Coronae. But from observational perspective, we know that we estimate that it's a large bunch of hot electron plasma surrounding the supermassive black hole. So in this figure, there is a supermassive black hole in the center and a accretion disk in the blue. And this diffused plasma is the corona, which consists of some tens of keV hot electrons and also positron and protons. And how do we see the X-rays in the AGN? So the accretion of the supermassive black hole will produce UV and optical photons, which will be upscattered by the hot electron in the corona to the X-ray emission through the inverse Compton scattering. So the UV photons to the X-ray. And also there are some reflection emission from the disk and to our outside. But today we are focusing on the intrinsic coronal emission from here. So what do we know about the corona? We know that it's a condensation process. And so we use a condensation model to describe or characterize the corona X-ray spectrum. So this is a spectrum of the corona with different corona temperature from 15 keV to 100 keV. So this is 100 keV and 15 keV. You can see that with a different corona temperature, the high energy photons, X-ray photons, will be less and less. And so there is a cutoff feature which depends on the corona temperature. And so in the observation, we use this kind of cutoff to derive the corona temperature of different variety of the AGN in the universe. So how do we probe it? The cutoff, as we can see, is about 100 keV. So we need a high-redshift telescope. And so we use NuSTAR, which is the first NASA-focused high-redshift telescope, launched in 2012, and its bandpass is from 3 to 80 keV from here. And this is China. And so in the local universe, NuSTAR has surveyed more than 200 AGN in the past. And we derive the corona cutoff here in this plot. And you can see there are a lot of lower limits. This is because in the local universe, the NuSTAR coverage only can capture the cutoff feature for the very hot corona. For the very low temperature corona. For the hot corona, it can only measure the continuum rather than this curvature, the cutoff. So that's why we see the lower limit in the local universe that can be measured by NuSTAR. So what can we do? We can go to the high redshift because the X-ray spectrum can be shifted to the lower energy band. The intrinsic, intrinsic X-ray spectrum of the corona can be redshifted to the lower observed energy band, so that this curvature will be covered by the NuSTAR bandpass, so that we can measure the corona cutoff of even the much higher energy or hotter corona. So this is our goal. That our the reason why we start this program to study the corona property of the high redshift quasars. So in the past 2 years, we accumulate 13 redshift about 1 radio quiet AGN using 35 days of NuSTAR data and 7 days of XMM observation. And you can see this is the result of our high redshift sample in orange. And a few sources are in the line system. So I plotted in the square, and for those unlined sources system, they are in the circle. And you can see that the majority of our sample, they have constrained corona cutoff. And for those 3 that have not constrained over lower limit, it's because their flux is much lower than we expect from the previous observation. So when we do the NuSTAR observation, its flux decreased by even 70% compared with its previous archival Chandra or XMM observation. So that's why we get a lower limit. But if we have enough photons, so we can still constrain them because they are shifted. But still, their lower limit is well consistent with what we measured. And the average is about 80 keV for the cutoff, and which is about 20 or 15 keV for the kernel temperature. And compared with the local sources, the average is 100 to 300 keV. And because they are mostly lower limit, so we don't really know, like the exact value. So the high redshift sample really give us a real, like a great statistic sample to study the corona temperature or cutoff, this cutoff feature. So how do we explain this temperature? It's pretty low. I mean, imagine that this is about 20 keV of electron plasma, and you observe the whole X-ray from like 0.1 keV up to 200 keV. So this 20 keV corona temperature is pretty low. And how do we understand this? One solution is that maybe one question we want to ask at first is the corona a purely thermal, or it has some fraction of non-thermal electron in the plasma. So to have a balanced corona, the heating process is through the magnetic field reconnection or the turbulence. So the accretion power will goes into the corona and heat up the corona electrons through this two process. And then there's the cooling process, which is through the inverse Compton scattering. That's the UV and optical photons cool down the hot electrons in the corona. When the heating and the cooling power are kind of balanced, you'll have an entire thermal distribution. So you see the Maxwellian distribution of the electron population in the corona. But when the heating is much less or much larger than the cooling, then you'll have some non-thermal tails. So for example, here. So when the corona is in a thermal distribution, you'll have this peak and with Maxwellian distribution, this blue. But when they are not balanced, there are some kind of non-thermal electrons in the corona. You start to see some non-thermal hardtails here, and this parameter can tell you what's the fraction of non-thermal electron. So the non-thermal electron fraction, non-thermal electron divided by the total electron population, and this is the non-thermal fraction. And why do we care about this hardtail? It's produced pairs. So with the normal, Maxwellian distribution, and when the electrons are high energy enough, the photons it produces will be at a few hundred keV. But when the electron is hot enough and the produced photons goes up above 500 keV or MeV, then the two photons can become electron positron pairs. And this electron positron will go back to a corona and then cool down the entire corona, the other population of the corona. So what happens is that you have some high energy electrons in the entire corona population, and then produce some really high energy photons, and produce some very low energy electrons. And these low energy electrons can cool down the entire corona electron population. So you see some low corona temperature. So that's how people find this kind of non-thermal hardtail can explain why the corona has low corona temperature. And so in this figure, it shows what is predicted. At different corona non-thermal electron fraction from 1% to 33%. And it's we plot here the corona temperature versus the compactness. So the compactness is the luminosity of the corona, or actually corona emission, divided by the corona size, which we assume now 10 Rg, the 10 gravitational radius, because the current measurement of corona size can only be taken using the microlensing method, which we in the high redshift, when the lens has the same size or similar size with the corona size, then we can see this kind of magnification process. Using this microlensing process, we can measure relative what's the size of the corona. And in silent high redshift samples, we find the corona size is about 10 Rg to 100 Rg. So here we use 10 Rg to do this kind of simulation, but we can choose 50 Rg. But here what tells us is that at high this value is luminosity divided by Rg, and because by the size. And now we use 10 Rg, so it's proportional to the luminosity of the corona. So at higher luminosity, the corona temperature should be lower. So what's this hybrid thermal non-thermal electron model predict that the corona should be on this kind of line, that at high luminosity it should be at low corona temperature. At low luminosity it should be with higher corona temperature. So at different electron non-thermal fraction, you can what you can do is that you can put your source on this kind of figure, and then what's the temperature, and what's the luminosity, and then what's the non-thermal electron. If all the sources you find is on this line, it suggests that it's a pure thermal corona. But if it is here, then it suggests us that there is a huge amount of non-thermal electrons. And we know that the non-thermal electron is produced by some instantaneous magnetic field reflection or very strong turbulence in the localized regions in the corona. So that suggests that the corona is really dynamic and variable, and have some instantaneous process. So this will be very interesting to probe. And here is our data. This is the local sources. and I plot the density of what we measure in the local universe. And these sources are the sources with constrained coronal temperature and also the luminosity. And because 75% these sources have only lower limit of coronal temperature, so the majority of sources are actually can be anywhere here. So it didn't tell us really, what's the non-thermal electron fraction in this hybrid model, prediction. And for these sources, for those with constrained coronal temperature, you can see that we need really high fraction, 33% of non-thermal, to explain a fraction of these sources. But the majority cannot be explained. In the high redshift universe, high luminosity sources, this is even extreme. The majority of our sources is here. So they have similar, compactness, but they need even more non-thermal electron. But reason we plot only 33% non-thermal fraction is that if they are more than 50%, can you still use this kind of, thermalized distribution to characterize the entire, the X-ray spectrum? So we know that we need really high non-thermal electron fraction, or this kind of model, does not work. So what can we do? So there is another parameter may help us to control this kind of the prediction of the compactness and the temperature parameter space. That there is a parameter called the heating and the cooling compactness ratio, which is proportional to the heating power luminosity of the corona divided by the cooling power of the corona or the luminosity. And it's proportional to the corona luminosity from we assume it's from 0.1 keV to 200 keV, which we can measure, and divided by the disk luminosity, which produce the photons, the soft photons that can cool the corona. And the disk luminosity is kind of the volumetric luminosity we measure in the SED of the agent. And this value for the local universe, for the local sources, is about 0.5 to 2. And so this figure here, we use this value of 1 to do the modeling. So without this kind of this figure, the prediction here should explain the majority of sources in the local universe, but it didn't. And more extreme, in the high luminosity sources, this value is about 0.1. And we plot this figure, try to explain what can be, what if they can explain the high luminosity sources. But still, this is a huge off, even at really high non-thermal fraction. So here is our conclusion on this hybrid non-thermal thermal electron corona model, that it's either we need a huge amount of non-thermal electron, which can make the whole corona, non-thermal, or not balanced, or we need extreme UV and UV and X-ray luminosity difference, or this kind of compactness value, which may not be explained by what we really measure.
But Xiurui, maybe I missed something. That L there is luminosity divided by
the corona size.
Yeah,
Yeah.
and that's an assumption. How strong is that assumption?
We think, this is you mean the corona size?
Yeah, luminosity measured, but
Yeah, the corona size, they all calculated using 10RG. So everything is
right, but
yeah.
if it's not the same, or it's different from the G, then that L, small L,
can be different.
and the points can go up.
Yeah, that's a good point. What we think is that the region that receives the soft photons from the disk should be the same region that produces this kind of X-ray emission in the corona. So the size, at least in this space, should be cancel out each other.
That's how you move.
Yeah. So Yeah, I mean, indeed, we don't really know the corona size of each source, but in this calculation, everything we use 10 RGs should be self-consistent. But anyway, is there other solution? We can try to explain the low energy of a low temperature of the corona. So with the GRMHD simulation, there's no beta, there's no button. It's GRMHD simulation. What we find is that at 7% enter ratio, the corona, the hot electron population, the temperature is larger than 10 K. But at high enter ratio with 0.2 enter ratio, the average temperature is about 10 K, which is in agreement with what we find that the corona temperature of our sources is about 10 to 20 K. But here, there is also a question that this is in the geometry simulation. So it doesn't really include the pair production, and also everything is calculated in small box, and they assume thermalization. So in their small beams, everything is thermalized instantaneously. So there is no non-thermal electron or non-thermal process in the simulation. And more importantly, there is no way that we can extract the spectrum of the simulation, the actual spectrum of the simulation, so that we can compare with the real world measurement. So they are still trying to do some other kind of simulation or approximation so that they can bridge the simulation to the observation, but it's still under development. But this kind of GFG simulation can self-consistently explain why at high redshift, a high ratio, we have a weaker corona. That what we observe is that at higher luminosity, the corona contributes less and less to the entire galactic. Yeah, so the take-home point is that at high redshift, we can mostly constrain the corona temperature or cutoff, so it provides a sample to systematically study the electron population in the AGN corona. And with the current hybrid electron model, the high redshift luminous AGN, or even a part of the low redshift low luminosity AGN, cannot be explained unless we have really extreme conditions like a very huge non-thermal electron fraction or very extremely low this kind of hard to soft compactness ratio. Or alternatively, we can use through the geometry simulation, we know that high enter ratio or high velocity sources AGN should in principle has lower corona temperature, but we need some like a spectrum to bridge our observation and simulation. And another work we have recently is that because this kind of hybrid model predict that the source should be on this kind of line with the same like a thermal fraction, and we monitor two sources which have already really good corona temperature constraint before. And when the source is more and more bright in one day, and then we observe it with NuSTAR again to measure its corona temperature, so we can tell if it is on this kind of like line, so that we can understand the fraction of the thermal electron and if the hybrid model is valid or not. And yeah, that's all. And yeah.
Great. Questions?
How good is the approximation that the corona has only a single temperature? Doesn't it get cooler toward the edge or something? The conductivity may be very high, but.
Yeah, I mean, this is a fantastic question. Last week when I visited the theoretical energy group at Columbia or at CCA, they showed me some simulation of what the accretion disk should look like around supermassive black hole. And the corona actually just the hot electron on the disk, on the surface of the disk. And in their simulation, the disk accretion is so turbulent. So the hot electron is also very turbulent. And they should be clumpy, they should be very turbulent, and they should be very inhomogeneous. So this kind of feature, I mean, this kind of cartoon, just a really, OI model can help us easily to produce some actually model to reproduce the spectrum. But in real life, everything should be turbulent everywhere. Yeah, the temperature of turbulence can be very different because the magnetic field, it can be very different everywhere, and the reconnection can happen anywhere. So it's very difficult to really, make it one homogeneous temperature. So what we measure actually just the effective temperature of the hot electron population. So everything I should say is the effective temperature.
Any other questions? I think we all have questions.
But
Or Nora, and then
For the two data points that you showed on your, I think, next to last slide. Yeah. How were the compactnesses measured in those two objects?
That's a good point. I mean, these sources, we don't really know the size.
Yeah.
So that can be a problem.
Just note that the error bars are teeny tiny, so.
Yeah, that's a good point. Actually, it can be, so I think this is more kind of priced on whether at higher luminosity do we get lower temperature, which is also, the general prediction of this hybrid model. So that's more qualitatively can tell us, but quantitatively I totally agree that we cannot really have a good accurate measurement. And not to mention the huge uncertainty on the black hole mass, that's another problem. But we have is really accurate measurement of the temperature that is can be with the good data.
yeah, nice talk, thanks. The process that you mentioned to generate the non-thermal electrons should, like reconnection, should also accelerate ions, right? So
Yeah.
which will enter your energy balance and your parameter as non-thermal.
Yeah.
So have you considered this effect, how this effect can influence your compactness versus coronal temperature?
Well, I mean, in the simulation here, it includes all the proton ions and also, I mean, their exchange of energy and also the lepton proton exchange of energy and also the photon exchange. So and also the gravitational effect also considered. So,
But you don't have the energy going to the ion acceleration. You just do thermal population, right?
yeah, kind of. So it's not really. I'm not exactly sure. This can be a good point.
Have you considered looking at more nearby sources? Cygnus X1, the black hole exobinary, has also a non-thermal tail. Can you estimate where on this plot it may lie?
Wow, that's a good point. At first, I mean, like the corona should have similar or like a region or on the surface of the accretion disk in the black hole binary. So we should be able to bridge this to the black hole binary. However, you have very different scale. Yeah, your question is
whether your model basically could also explain the non-thermal tail in Cygnus X1.
Yeah, that's a really good point. One of the prediction of this hybrid model and why it's widely accepted is that this non-thermal tail actually is a high energy electron, which by naturally it predict a hard X-ray tail and which cannot be explained by the power law or the black body produced by this thermal part. So I think it's definitely can, if you have the entire spectrum with the actually produced by the thermal part, and also you can observe this non-thermal part, that will be extremely help you to extremely helpful to constrain, you know, this non-thermal phase. And in AGN we are not able to observe this non-thermal hail because the NuSTAR observation above 24 keV is extremely, you know, like obscured by the background of the NuSTAR. So far not in AGN, but in black hole binary, that's super interesting.
I guess just one final question. So for the microlensing work, and you know, these sorts of suggest that the corona has an extent of 10 RG. So how sensitive is that result to the assumptions on the accretion model?
Wow. I mean, like what they measure is the real physical size. So of the corona. So what they really measure is like in centimeters.
Yeah.
Yeah. So
Okay.
yeah. So that's very accurate.
Okay. And have you thought of testing how the compactness and things like the luminosity changes as a function of the mass accretion rate? So like, you know, whether this suggests that there's a cosmological evolution of what the corona is doing or its properties,
Yeah, that's great.
because you have these lens quasars. So.
Yeah, that's a great point. For the lens quasar, I would say the size of the corona can be well measured, but their luminosity is very uncertain.
Okay.
Yeah.
Like the
intrinsic luminosity, especially at different wavelengths, the lens magnification factor is very different because you need the different structure to magnify. That's sure. So that's why next step we want to observe only the unlensed sources.
Okay.
Yeah, that's
Okay. Thank you so much.